structure of methane. It's got a central atom and 4 bonding pairs. Ammonia has a central atom and 3 bonding pairs and a lone pair around the central atom. And water has 2 bonding pairs and 2 lone pairs. Now, what is the similarity in those 3 structures? What is the similarity? Sorry?
There's 4 bonds, there's 5 different points.
Well, 4 different points.
Oh, I'm sorry. Yeah.
So here I've got 4 bonding pairs, here I've got 3 bonding pairs and 1 lone pair, and here I've got 2 bonding pairs and 2 lone pairs, but it all sums to 4. Mm-hmm. They all have the same, what we call electron pair geometry. Electron pair geometry or electron group geometry, tetrahedral. But they have different molecular geometries. So an electron pair geometry is literally, as it says, it's the geometry of the electron pairs, bonding and lone pairs. But then we have molecular geometry too. So here we've got a molecular geometry that is tetrahedral, if the thing looks like a tetrahedron. The molecular geometry here we call trigonal pyramidal, and here it's bent. So we distinguish 2 things with VSEPR theory, very important. Electron pair geometry and molecular geometry. Right? And so these 3 molecules have the same electron pair geometry but a different molecular geometry. And this is very interesting because you can see if we, sorry, there's a bit of a mess up here. Those 2 lone pairs should be on the oxygen. But these are the actual bonding parameters of methane, ammonia, and water. And what do you notice? What do you notice to the bond angles?
They're different.
Correct. It goes from 109.5 to 107.8 to 107.3 to 104.5 in water. Right? Why? Because we introduced a lone pair here, and that lone pair actually increases the repulsion between the lone pair. Well, the lone pair bonding pair repulsion is higher than bonding pair repulsion, and that sort of forces the angle to get squeezed inwards. Here we've got 2 lone pairs on the oxygen, those should be on the oxygen, and that pushes these bonds in even further. So this is what VSEPR theory is all about, right? It's about positioning bonding and lone pairs as far away from each other as possible around the central atom, and then depending on what you get, you can not only predict the geometry, but you can also predict, sort of say something about the relative bond angles. And so these 3 belong to the same family. They all belong to the family of tetrahedral electron pair geometry molecules, but they have different molecular geometries, tetrahedral, trigonal pyramidal, and bent. And on the basis of VSEPR theory and on the basis of the fact that lone pair repulsion is greater than lone pair bonding pair repulsion, which is greater than bonding pair repulsion, I can actually make some estimates as to what the bond angles are going to be. I have to continue. Keep your question for the end. So that's the story. VSEPR theory can give us this information and guide us and explain why we have these changes in the bond angles, right? It's because of this repulsion. Now this is the overall picture, right? Let's go through this. We start off with linear, where I've got a central atom with 2 groups around it, right? We talk about an electron group geometry and molecular geometry. Now there's only one possibility there. So if I've got a central atom with 2 groups around it, it's going to be linear. Okay, that's like an example is beryllium dichloride. Okay, let's go to this case here. I have a central atom. So now check this out. Check out what's happening here. I have a central atom, and I have 3 groups around it. Those 3 groups can either be bonding pairs or electron pairs, okay? In other words, it can either have a central atom with 3 atoms around it, or with, 1 atom and, 2 atoms and 1 bonding pair, whatever. 3 electron pairs around the central atom, and we call that as an electron group geometry that we call trigonal planar. It's flat as a pancake. Now, watch what I do. I replace one of the atoms with a bonding pair, and I end up with a bent geometry. So this is the molecular geometry. This is the electron group or electron pair geometry. Boron trifluoride is an example. We just had that example. There's a ball and stick model of boron trifluoride, right? It's flat as a pancake. Its electron pair geometry is trigonal planar. Its molecular geometry is also called trigonal planar. This guy here, sulfur dioxide, its electron pair geometry is trigonal planar. Its molecular geometry is what? Bent.
Isn't like the angle should be like smaller because of the...
It should be, you're right. On the basis of VSEPR theory, very good. We would predict this bond angle to be less than 120 because the repulsion between the lone pair and the bonding pair should be greater. VSEPR theory, again, is a model that makes predictions which don't always pan out. If you measure experimentally, it turns out the bond angle is 120, but you would predict it to be less. Okay, you're right, on the basis of predictions, very good. Right, but does everyone see a pattern emerging here, right? You always start off with the electron group geometry and then go to the molecular geometry. Here we have the family of four, we just looked at this tetrahedral, right, and notice the pattern. I start with four atoms, I start replacing them sequentially with electron pairs, tetrahedral, trigonal, pyramidal, bent. And here you can see, okay, these are the idealized bond angles. Of course, they're lower in reality. It's 107.3 and 104.5. So yeah. So we've just seen that. Now check this out. Okay. Now we get to this extended octet, right? This business of hypervalence, we can also call it, where we have more than 8 electrons around the central atom. In the case of having 5 groups around the central atom, I have something called trigonal bipyramidal geometry. Trigonal bipyramidal, that's what we call it. So, and these are the possible, let's say, deviations from that. So this is like this is the electron group geometry, and these are the possible molecular geometries within that family. Okay? So check this out. Here I have 1 lone pair and 4 bonding pairs around the central atom. That gives me a molecular geometry that I call seesaw. What is a seesaw? Something you have in a park, right? A seesaw. It's got a seesaw geometry, right? The example is sulfur tetrafluoride. What is the electron pair geometry of sulfur tetrafluoride? The electron pair geometry of sulfur tetrafluoride. Correct. Good. The electron pair geometry is trigonal bipyramidal. The molecular geometry is seesaw. This thing is going to look like a seesaw. The molecular geometry is the geometry of the actual atoms, not the lone pairs, okay? Now if I replace 2 bonding pairs with 2 lone pairs, I'm going to end up with a guy that looks like this. That's T-shaped. Okay, an example is CLF3, and so on. I can have 3 lone pairs and 2 bonding pairs, where I end up again with a linear molecular geometry. An example is xenon difluoride. Okay, so you must be able to do this. And the point is, if you cannot draw a Lewis structure, you've missed the boat, right? Because in order to predict the geometry, you need to have the right Lewis structure. The last thing is the family of 6. So sulfur hexafluoride. So these are all have an electron pair geometry which we call octahedral. Sulfur hexafluoride is an example where the molecular geometry is also octahedral. We have BRF5. This is an example of a so-called square pyramidal molecular geometry. Notice what I've done. I've replaced 1 bonding pair with a lone pair. And if I replace 2 bonding pairs with 2 lone pairs, like xenon tetrafluoride, this is a classic example, one of my favorites, you end up with a beautiful square planar molecule. And this is all on the basis of VSEPR theory, and the predictions pan out pretty well. So what you need to know is you need to basically know how to apply, once you've drawn the Lewis structure, use VSEPR theory to predict the electron pair geometry, also called the electron group geometry, the molecular geometry, and make some predictions about the bonds. Let's say I compare ammonia and methane. You know, which will have bigger bonding angles, using the principles of valence shell electron pair repulsion theory. And of course, you should be able to calculate formal charges, discuss resonance, and all that stuff. So this is all part of this whole picture. But if you cannot draw the right Lewis structure, you've missed the boat. Now there's just one final thing I quickly want to discuss, and that is dipole moments. I know I'm running over time, my apologies, but this will take 5 minutes. Dipole moments. Now we discussed earlier this notion of when a bond is polar or not. Okay, it depends on the electronegativity. A molecule as a whole can exhibit polarity or not. Okay, now this is a slightly more difficult concept. A molecule that's polar as a whole is going to be or interact with an electric field. If I have a polar molecule and I switch on an electric field, here I have, for example, OH minuses. They are polar, they have a positive polarized end and a negative polarized end, and I switch on an electric field, they're going to arrange themselves and align themselves with respect to that field. And if they do so, I can actually calculate their polarity according to this formula. The symbol for polarity is mu, okay? So polar molecules interact with an electric field because they have an asymmetric distribution of electrons around them. Now, here I have some molecules. Okay, these are polar molecules, chloromethane, water, and ammonia. We can measure the polarity basically by doing experiments as I've shown here. Right, you can actually just basically measure the polarity in Coulomb meters. Right, these units we also call debye. Right, this is the unit for polarity named after Debye, who was actually a scientist from this region. Right, he did this work in the United States, but he had his origins in Maastricht. So polarity is expressed in the symbol debye, as you've shown here. This is the symbol for polarity. And here we have some examples of polar molecules. Now what I've drawn here, these green arrows, are bond polarity vectors. So to figure out if a molecule overall is polar, overall, I have to take the molecule and I've got to look at each bond and see whether each bond is polar or not, and then take those bonds overall and sum them and see if I end up with a result or not. Now let's take, for example, chloromethane. That guy's definitely going to be polar, because if I add up these 3 bond polarity vectors, have you all done vector analysis? Vector algebra? Well, if you haven't done vector algebra, then just think about if you add those lines up, do you end up with a positive result, yes or no? Yes, you do. If you add these 2 up, do you end up with a result? Yes, you do. Because that's pointing up, that's kind of pointing up. They're both sort of pointing in the same direction. If you sum them, you're going to end up with an overall polarity. Okay? Now, this is the same with ammonia. These 3 guys are all pointing kind of up. So there's going to be an overall upward polarity. The whole thing overall is going to be polar. The point is this, and this is a difficult concept. It's possible for molecules to have polar bonds within them, but be non-polar overall. Let's look at an example of that. And that will be the end of today's lecture. Tetrachloromethane. Right, this is now, I've drawn the structure of tetrachloromethane in 3 dimensions using dotted lines and stuff. Now, tell me, a carbon-chlorine bond, this is carbon, this is, maybe I should just represent this a little bit better. So each of those bonds, that's a Lewis structure represented in 3 dimensions, it's tetrahedral. Are each of those bonds polar, yes or no?
Yeah.
Yes. There's a difference in electronegativity between carbon and chlorine. In fact, for the sake of illustration, let's do it a little bit more extreme. Right. So this is going to be negative. So each of these bonds individually are polar. Now the question is the molecule overall polar? Yes or no?
No.
No, why not?
Because if we add the sum of the vectors or forces, they all negate each other. Correct. When one is pulling on this side, the other one is pulling on the other side, and each one cancels each other.
Let's draw it. I can draw the bond polarity vectors in this way. For example, pointing towards the more polar atom, these 3 at the bottom here So the molecule is tetrahedral. Those three at the bottom are going to, if you sum them up, going to have a bond polarity vector pointing down, which is going to be sort of negated or cancelled out by this one pointing up, and so the polarity is 0. Another example, xenon tetrafluoride. Right, so xenon tetrafluoride. So the question is it polar, yes or no? Well, you can't just look at it and say, oh, it's going to be polar. What do you have to do? You have to first figure out what the molecular geometry is, and how do you do that? It all starts with the Lewis structure, exactly. So let's draw the Lewis structure. Xenon is a noble gas, and believe it or not, noble gases can also make bonds under certain circumstances. Typically you need light, pressure, lasers, etc. But you can get xenon and fluorine. If you take xenon and fluorine gas and you pass light through it, laser light or high pressures, you can actually get xenon and fluorine to form molecules like this. This is xenon tetrafluoride. It exists. Now again, that's the Lewis structure. Remember, we marry this. We marry these guys together. So sorry, there should be a cross here. So this is the Lewis structure for xenon tetrafluoride. Right. So what is the electron group geometry? Octahedral, correct. Correct, very good. What is the molecular geometry? Square planar. They're two different things. So it's a molecule that belongs to the family of octahedral stuff, octahedral electron pair geometry, but its molecular geometry is square planar. Now, the xenon-fluorine bond is it polar or not? Yes. This is certainly going to be polar. But is the molecule overall polar? No, why not? Because it's square planar, it's perfectly square planar, so this is easy to represent. This is xenon tetrafluoride. See? It's perfectly square planar, and with 90-degree bond angles. Each of these bonds are polar, and if I add them up, one after the other, I end up with where I started. The result is 0. It's non-polar. So polarity of bonds and polarity of molecules are two different things, right? That's very important. And to answer the second question is not trivial. You have to know what the structure of the thing is, which you have to figure out by VSEPR, which you figure out by first drawing the Lewis structure. You see, it's a chain of events. And if you get the Lewis structure wrong, then the house of cards collapses.
And for example, if like the angles are a bit like bent because of like unbound electrons.
In xenon tetrafluoride.
Yes, could it be like then that it, not in this case, but that normally if we show it normally without taking into consideration the non-bonding electrons, because of the bending part, could have a slightly polarized.
No, because it's always going to be a line. So whether you have,
but not for this case, but for in some.
Well, yes. I mean, you have to look at the individual geometry, and then you've got to sort of sum it vectorially to do it. Yes, it could be. But in the case of square planar molecules, they're never going to be polar unless I, for example, do something sneaky like this.
A CL.
Yeah, exactly. If I put a chlorine in there, will it be polar? Yes, it will. Because the difference in because this vector is not going to be the same length as that, so there'll be a slight polarity. Okay, and that's the end of today's lecture. I hope you all enjoyed it, and I'll see you later.
Yeah. By the way, thank you.
I did.
So you don't really mean it? I don't know. I don't even know. It's not even like notes. It's like, maybe. Martin dropped this one. Martin Parker. Martine. You dropped your Parker.
Come on.
Pick it up. Shit, cameras. Careful, don't move the thermometer. Yeah, it moved. The internal thermometer is going to mess up the spectral.
Thing now, so should be out there. But if not, we can just give it to them.
Is it going? Listen, you've got enough thermometer.
Because
Yeah, the last part was easy.
well, I mean, the thing is that most load cables sitting on it's hard. They're not. Load cables do not polarity is really a load method. You just think of it in terms of the bonds to atoms. That's what dictates polarity.
I thought it was good when you had it like that. Why do they not get with the hands and the box? So they'll be full really then in the lower.
Never got even to grab a jacket.
Because they cancel each other out. Because you can't, all of these bonds have exactly the same amount. So these two cancel each other out, and these two cancel each other out. So there's nothing. Also, there's no. It's cancellation effect. It's like if you walk 3 meters in this way, 3 meters like this, 2 meters like this, 3 meters, 4 meters, 5 meters. So back where you stop.